Hello students, welcome to the class. So today we will see the theory part 8 of the chapter 6 equilibrium, in which we will be covering section 6.11. So this is the disclaimer. Now in this class our objective would be, first of all, we will classify our given solutions as acids and bases on the basis of their strength. So if they are weak, we will term them as weak acids or weak bases, or we will term them as strong acids and strong bases. And this whole classification will be totally based upon a very important equilibrium constant, which is ionization constant. After that, we will look on to degree of ionization. So to understand this ionization constant in terms of degree of ionization is very important, and this will end up to a very important formula which we will see in this lecture. Completing this part, we will move on to a next very important part, which is pH scale. So it is basically a way to represent the hydrogen ion concentration. Now why are we interested in hydrogen ion concentration? We have seen so far that acids are mostly characterized by the H plus concentration, and same can be said for the base also in a way. So to give a specific way to represent this H plus concentration was very important, because H plus concentration has a very tedious way of representation due to its variance. So to represent it in a simple way, we have this pH scale. We will see on to it. Moving on to the next part, which is ionization of water. Now we are already dealing with water in most of our reactions, and we have seen that it can act both as an acid and base. But can it act as an acid and base for itself only? Means 1 mole of water will act as an acid and the other mole will act as a base in the water itself. So this is a very interesting reaction, and that will lead on to the ionization. We will see on to that also. And lastly, we will define the Kw and pKw for this ionization. So basically we will quantify this ionization of water. If I talk about the specific sections of the NCERT that we will cover, then obviously we will be covering 6.11, which is ionization of acids and bases, in which we will cover the first part, which is ionization constant of water. So this is the canonical order that we will follow. Now your water is itself a weak acid and also a weak base, so we will take it as an example, and we will have a specific ionization constant representation for this water thing. Moving on to the next one, which is pH scale 6.11.2. Third one is ionization constant for weak acids. So we will define it in a general way also. Starting from this specific water example, we will move on to this general way also, which is 6.11.3, and then we will explain the same for a weak base. Moving on to the last topic, which is relation between K and Kb. So I would say that this is the most important formula that you will see after your ionization constant formula for acid and base. So it will help you to calculate K or Kb knowing the other one for a given acid base pair. I will clarify this part. Now first let us start with the difference between ionization and dissociation. So before moving on to ionization, you should know what ionization is and what is the difference between dissociation and ionization. First, if I define dissociation, so it is basically the separation of existing ions in a compound. Now what is the meaning of this existing ion? If you consider an ionic compound, then it is already made up of ions. Now the moving apart of these ions away from each other is known as dissociation in a solution. For example, if you take a sodium chloride at a molecule, then not a molecule, I would say a formula unit of the sodium chloride, then this formula unit is already consisted of Na plus and Cl minus, which are its ionic form, right? And when you break these ions apart, or you can say when you overcome the electrostatic attraction between Na plus and Cl minus, then they are separated in a solution. This process is called as dissociation. If I define ionization, then the end product is same for the dissociation and ionization, but the start product is different. In the case of dissociation, if you see, we have started with the ionic compound, whereas in the case of ionization, we mostly consider covalent compound. Now you would say that there is never a distinct line between the covalent and ionic compound, but still you have a general idea, right? So you say that NaCl is mostly ionic, so we will move on with that sense. So that is the reason I have written it as often a covalent compound, right? So whenever you are separating the constituents of a neutral molecule, which is a covalent compound, and you are forming ions from it in a solution, then you call this process as ionization. What examples can be thought of? Say we have this HCl. Yeah, now you know it very well that this HCl is not an ionic compound because it is made up of two non-metals, which is hydrogen and chlorine. So this will surely make up a covalent compound. But still, this thing goes into the solution and gets completely dissociated, as it is a strong electrolyte, to give you the hydrogen plus, which is hydrogen ions, and your chloride ions. Is it clear? So the difference should be clear between dissociation and ionization. Now we will move to the ionization part. So first, we will look on to the strong acid base categorization on the basis of ionization. How we will categorize them? So this can be explained through two theories. First is your Arrhenius concept, and second is your Bronsted concept. According to Arrhenius concept, the strong acids are substances which completely dissociates in water to give H3O plus. Means you will not notice a single undissociated molecule or formula unit in case of strong acid. For example, you can think of HCl, it completely dissociates into H plus and Cl minus. Now you will ask why we are not writing H plus and instead we are writing H3O plus. Because we know it very well that H plus is not stable. To make it stable, we keep it in a hydrated form or we react it with water to give H3O plus. So that is the reason we are writing it as H3O plus and not H plus. Similarly, if I define base, a strong base according to Arrhenius concept, then these are those substances which completely dissociates to give you hydroxide ions or OH minus ions. So this is the definition of strong acid and base according to Arrhenius. Then if I try to define strong acid and base according to Bronsted-Lowry concept, then it says that strong acids are those which are good proton acceptor. So this may put you in a dilemma. What is the meaning or what is the extent of good proton donor? For that reason, I would suggest you that to decide strong acid and strong base, you mostly go with this Arrhenius concept because you know it very well what are the substances that completely dissociates, at least in most of the cases. But still, you need to know the Lowry concept as well. So it tells that a good proton donor is considered as a strong acid, whereas a good proton acceptor is considered as a strong base. You would ask me that why we are saying it in terms of Arrhenius is because if you consider some examples, say we consider HCl, you know it very well, that is HCl is completely dissociated, but you don't know that whether it's a good proton donor or not. I hope this categorization of strong acid and base is clear to you. Now moving on to the weak acids. So we are also interested in comparing weak acids, that which one is stronger, although weak acids are those which dissociates up to a very small extent, but in that also there is a competition of this extent for different acids. So we will understand this with the help of example. Now remember, before moving on to the example, remember one very important line, and I will prove this line also, that reaction always proceeds towards the formation of weaker acid. So this is the most tagline statement for this comparison of weak acids. Now, Let us start with the acid-base dissociation of a weak acid written as HA. If you write this HA dissociation in water, then you will see that HA reacts with water to give this H3O plus and A minus. H3O plus is the conjugate acid of this H2O base and A minus is the conjugate base of the HA acid. We are into defining the comparison of the weak acids. So to compare that, we will look that which one is a weaker acid. Either on the reactant side we have this HA, on the product side we have this H3O plus. So the extent of equilibrium or the direction in which your equilibrium will go will depend on the weaker acid, and for that we have to compare these two acids, HA and H3O plus. So let's look on to that. Case 1, we are taking that suppose HA is a stronger acid. What will happen? If HA is a stronger acid, then HA will dissociate more or it will give more proton. So the reaction will move where? Onto the right hand side. So this is the reason I am saying that the reaction will always proceed in the weaker side or on the weaker acid side. You can see it clearly from this statement that if we are considering H3O plus as weak acid, then the reaction is proceeding towards the weak acid. So as a result, HA plus will donate more and more proton, leading to the formation of H3O plus, therefore putting the reaction in the H3O plus side. In the second case, we are considering HA is a weaker acid. So where will the reaction go? It will go towards the reactant side. Why it is going? Because now the H3O plus will donate more protons and reaction will be favoring your formation of HA, because now the A minus will get more and more proton that will convert into HA. Is it clear? So this is the reason I was saying that reaction will always proceed to the formation of weaker acid. This was the reason we were seeing the Bronsted-Lowry concept. To compare the weak acids, it is very comfortable to deal with this Bronsted-Lowry concept. Okay. Now we will look on to a small aspect of this ionization of acids and bases, which is indicator. What is this? Let me introduce you to what is indicator. So they are substances which shows different colors in acidic form and basic form. Now this definition is very specific. There is a broader sense to the term indicator, but we are now interested in your syllabus. So we will keep our definition or keep our perspective only up to color. So how do we understand this? So let us take an example. Before moving to that, you should remember that these type of indicators are mostly used in acid-base titrations. Now let us look at an example. We said that we have an indicator and we are representing the acidic form of that indicator with HLN and the basic form with Ln minus. It is seen that indicators are those substances which show different colors for the acidic and basic form. Right? Suppose we have this HLN and we are reacting it with water. Then you will see that the aqueous form of this acidic nature, which is HLN, shows color A, and the basic form, which is Ln minus, will show color B. How can we understand this same equation? By looking at an example of bromothymol blue. If you look at this image, you can see that it has three different colors. If you are keeping this, say your bromothymol blue in acidic system, then it will show a yellow color, right? If you are keeping it in a basic solution, then it will show blue color, and the case of neutral one, it will show a green color. So you can see and look at the importance that how it is very useful in determining the nature of a given solution. Now moving on to the next part, which is auto-ionization of water. So this is just a specificity of this ionization of acids and base. Now we know that water is a very weak electrolyte because it is not completely dissociated in any polar solvent. At the same time, it is amphoteric, means it can act both as an acid or base. So, the autoionization of water means your water itself react with another molecule of water to form hydronium ion and hydroxide ion. So, this is a very unique nature shown by water. In this reaction, one molecule of water donates a proton by acting as an acid, whereas the other molecule of water accepts that proton acting as a base. If I put the same thing in an equation, then you can see here the acid part means the acid water is donating one proton and becoming its conjugate base, which is OH minus. At the same time, your H2O is accepting that and becoming its conjugate acid. So this is a very beautiful representation of autoionization of water in a single equation. Now if I ask you, can you define the equilibrium constant for the reaction? Yes, it's very simple. We can write Kc is equals to concentration of product, which is H3O plus and OH minus, divided by the concentration of water square times, because we have 2 moles of water on the reactant side. If we continue with this equation, then we can define a very important term, which is ionic product. Now this ionic product is being defined in this case, if I say at 298 Kelvin. Now it can be defined at different temperature. The definition will remain same, but the value will change. So that is the reason I am writing it as 298 Kelvin. According to this ionic product of water, you can take the concentration of pure water obviously as constant, because the ionization is not that much significant. So we can further take this H2O concentration as constant and multiply it with the Kc. If you incorporate this, you will get Kc into H2O whole square is equals to H3O plus concentration multiplied by OH minus concentration. At this point, we will define our ionic product of water Kw, which is equals to Kc multiplied by H2 whole square, and it is equals to the H3O plus OH minus. So this is the main formula for Kw calculation, which is multiplication of the H plus concentration or H3O plus concentration with the hydroxide ion concentration. I said you that we are going to define a definite value for this Kw at 298 Kelvin. So that is totally based upon experimental values of the hydronium ion concentration and hydroxide ion concentration, which is equals to 1 into 10 to the power minus 7. So this is the experimental result for the concentration of both the hydroxide ion and the hydronium ion at 298 Kelvin. We will substitute this back in the above equation 6.27 to get the value of Kw as 1 into 10 to the power minus 14, and mole squared will be giving you the unit. So this is your final equation 6.28. So this is a very important result for the autoionization of water, and the value which is written here is used often. If I further move with this equation, then we can define a new term, and you will be seeing this kind of similar term for various other constants. Means this p term here that you are seeing, you will verify that there are numerous number of p terms for different constant. First we are defining it for Kw. How we define it, and the way of defining is always same. You will see that H plus concentration is taken as pH in the same way, K is taken as pK, and similarly your Kb is taken as pKb. How is the definition written? Very simple. We know that Kw is equals to hydronium ion concentration multiplied by hydroxide ion concentration. In this, if we take a negative log with a base 10, then what we can write? We can write Kw with a negative log as pKw. So this is the definition that you will see. Only this Kw will vary. In some cases you will see H plus on both sides. In some cases you will see K, Kb, but this definition will remain same to define the p term. At 298 Kelvin, we know that this value is 10 to the power minus 14. If you put this value here, then pKw will be taken as 14. How are we saying it? Because the base is taken as 10, right? So we have taken a negative logarithm with the base 10. Now log 10 raised to the power minus 14 can be written as minus 14 on the product side, or you can say we will multiply this log 10 with a minus 14. So this is a general property of log. Log a to the power b can be written as b log a, right? Now log 10 is equals to 1, therefore it is finally equals to 14. Got it? So this is your way to calculate the pKw at 298 Kelvin, which is 14. Moving on further, let us look on the effect of temperature on your Kw. We know that Kw is nothing but an equilibrium constant. Obviously, it will have the impact of temperature change. First thing you should know is that ionization of water is an endothermic process. So you need to break your water molecule into ions. For that you need energy. Therefore, it is an endothermic process. If according to Le-Chatelier principle, if you supply energy, then to break this energy, I would say to consume this energy, the system will restore equilibrium by consuming this part. And you know it very well that the reaction can only consume this extra energy if it moves in the forward direction, as it is an endothermic process. If it will move in the forward direction, that means the product's concentration is increasing, or you can also say the Kw value is increasing, because Kw is nothing but the concentration terms product. So this is a very important point, and it is used in the numericals as well. So if you are seeing a Kw value at different temperature, then you should use that value instead of 14. So that 14 value is only defined at 298 Kelvin. Second thing, it depends upon the nature of solvent. If you are taking a neutral one, then the concentration of both OH minus and H3O plus will be same, right? If you are taking an acidic one, then obviously your H plus concentration will be higher, or your hydronium ion concentration will be higher. Whereas in the case of basic solution, OH minus will have a greater concentration. So this is the parameter for defining the nature of a solution as well. Now we will move on to the next important topic, which is pH scale. As I said you in the start, that this pH scale is nothing but a way to define acidity of a given solution in terms of simpler values. How do we define it? So to define it, we again use this P term. We take the negative logarithm of the activity of hydronium ion. Now you will ask me that what is this activity? So this activity is much more closer to concentration. And in your 12th standard, you can simply consider your activity is equals to the concentration, right? Because in most of the solution, we take a lower concentration so that activity does not deviate from concentration. So this part you must know. That's enough for your 12th standard. Now, if you know that your activity is equals to concentration, then what we can say that for dilute solution, if you are defining the activity of hydronium ion, then it will be simply equals to the concentration of hydronium ion. Further, taking negative log with a base 10, what we will get? We will take pH is equals to minus log activity of H3O plus is equals to negative log of hydronium ions concentration. Now we know that from the definition of pH that negative log of the activity of hydronium ion is equals to what? It is equals to pH. Further, we can remove this thing, activity thing from the middle, and finally we got our pH formula as minus log H plus or H3O plus concentration. So this is very, very important formula for your pH calculation. Now similar to pH, we have this P thing for the OH minus concentration as well. How do we define it? So we write it as POH is equals to minus log of hydroxide's concentration. So these two formulas are used, and at 298 Kelvin, what will happen? The pH and POH will have a summation of 14. So that is the part which is used in most of the numericals. and this value can change with temperature. You should remember this thing also. Here is a very important takeaway note for you. Although you are seeing a very small change in pH, but at the molecular level, there is a drastic change in the H3O plus concentration. So your H3O plus concentration will be changing not by just 1 unit, but by a factor of 10, because we are taking a log of it, right? So this is very, very important to remember. And in the numerical part also, you will see that options are very close to each other. So you have to choose the appropriate option, because changing the unit, changing the number even by a very small value can change your H plus concentration significantly. Now moving on to the next thing, which is relationship between Kw, pH and pOH. We know it very well that Kw is equals to H3O plus concentration, OH minus concentration. We have already derived it for water. What can we say further? That if you take the negative logarithm of these three, then your minus log Kw can be written as P term, which is pKw, minus log hydronium ion concentration can be written as pH, and minus log OH minus concentration can be written as pOH. We know it very well. Further, the second thing that we know about pKw value is your 14 value, right? So we can write whole as pH plus pOH is equals to 14. So I've mentioned this part in the previous discussion. So here it is coming from, right? That pOH plus pH is equals to 14, and this is only true at 298 Kelvin. Let us move on to the categorization on the basis of pH. We have seen that we need to know the H3O plus concentration or OH minus concentration to define it as acid or base. But at the same time, we have the difficulty of these tedious values. So what we are doing now, we are defining the acidity or basicity of the solution on the basis of pH. For example, if your pH is equals to 7, right, at 298 Kelvin, this I am saying it at 298 Kelvin, then your solution will be neutral. At the same time, if this pH value is less than 7, then the solution will be acidic, and if it is more than 7, then it will be basic. You can try and derive these relations. So these are very important, and you can derive it very easily by using the concept of pH plus pOH is equals to 14. Here is a way to calculate, or you would say to analyze a certain range of pH, which is pH paper. Now this pH paper consists of dyes, and these dyes have a special property of changing color according to the pH value. Now when you dip this dyes into your specific solution in which you are interested in, then by looking at the change in color, you can determine that what is the nature of the given solution. Okay, and without going into the molecular level, you can quickly measure the solution's acidity or basicity. So here is an example of this. So these are some strips that you are seeing. The first strip, second strip, third strip, and fourth strip. So those either of these 4 strips can be used for acid base determination. So you can use the first one also. You can see that in the first one, it is having a yellow color in 0 pH, and slowly it is going to purple color. Now some dyes have a different property. It is initially purple, but after some time when you go to the basic part, you see a yellow color. Similarly, you have this second and third strip. I hope this pH part is clear to you. Now next thing which we are interested in is the Ka value. So we have already seen the ionization of weak acids, how it happens, but the problem is that only the qualifying is not important. We also need to quantify it. Okay, so let's see how do we quantify it. So the term that is used for it is your acid dissociation constant, and it defines the strength of an acid and base. So if you know K value of 2 given solution, then you can compare their acidity very easily. So if I consider the weak acid, then we know that this weak acid ionizes partially in water, and this value of K is also relevant to weak acids only, because in the case of strong acids, we know that the ionization is complete. So we don't have a equilibrium situation, or you can say not, I would not say equilibrium situation, there is no undissociated or dissociated part. All parts are dissociated until and unless there is no dissolution. So if there is a complete dissolution, then strong electrolyte will always show complete dissociation, right? So this Ka terms is much more relevant to your weaker acids, and it is never used for strong acids. Say we have a weak acid Ha. How do we write the dissociation of this weak acid? So this will suppose react with water to give you H3O plus and A minus. We have seen this equation. Further, if I ask you, can you write the ionization constant, acid ionization constant for the above reaction? Yes, it's very simple. How do we write it? We simply take the concentration of the product divided by the concentration of the acid. Now you will ask me, why am I not considering the H2O? Because H2O is something which is constant. So therefore, we are multiplying this equilibrium constant Kc for this equation with H2O to give this K. Further, again we take this negative log base 10 to define our P term for Ka, which is Pk is equals to minus log K. Now you have seen three types. First, you have seen this Kw, which is pKw. You have seen H plus, which is pH, and Ka, which is pK. So, what is the effect of this K and pK? How do we differentiate the acidity or compare the acidity with the help of Ka and pK? So, if your acid is having a higher K, that means it is dissociating well, and hence it is a strong acid. If it is having a higher pK, that means it is a weak acid. So pK is opposite of K. How can we say it? Because it has a negative against K log. Got it? So if you want a stronger acid, then it should have a lower pK. Now we will look on to this weak acid ionization in terms of pH. So first we will define K and make it suitable. So to define it suitably, we are introducing a new term, an important one, which is degree of ionization. Now what is degree of ionization? So don't panic with this terminology. It's very simple. It is just a fraction of the dissociated part, right? Suppose you have a cake and it is divided into 6 parts. I said that I have eaten one part. Then if someone asks you that what fraction of the cake is left, you will say that, okay, we have 6 fractions in the starting and 1 is eaten, that means 5 is been left. So the left fraction is 5 by 6. Similar to that, we have this fraction of left part, ionized part. Similarly, we have a fraction for the dissociated part, which is simply the total number of moles in the denominator with the dissociated number of moles in the numerator. So we can define a formula for alpha, which is degree of ionization, as moles of acid ionized divided by the total moles of acid. If we are defining it for a acid, let's assume that C is the initial moles of acid, right? And X is the moles which is ionized from this C after reaching equilibrium. Then how can we write alpha? Very simple. What was the initial number of moles? C. And what is the number of moles that is being ionized? It is X. So alpha will be X by C, right? Or you can write this concentration, or I would say not concentration. You can write this initial number of moles in terms of what? Alpha, which will be X is equals to C alpha. C is equals to alpha X by alpha. At the same time, we can write the number of moles dissociated in terms of alpha, which is X is equals to C alpha. So you can say that after your equilibrium is reached, C alpha amount of molecules is getting dissociated, right? Because it is equals to X. Now remember this situation. Now we will apply that same situation onto this general case where we are considering again HA as a weak acid, which is dissociating to give H3O plus and A minus. So can we write K for this in terms of alpha? Let's see. If we assume that C is the initial moles of this HA at T is equals to 0, and X is the total moles of HA that is dissociating at equilibrium. So from the definition of alpha, what we can write? That X is equals to C alpha. Got it? Further, what will be the number of moles of reactant that is not dissociated? So initially if we have C moles, and if C alpha is dissociated, then the total number of moles which is left will be C minus C alpha. So that is very obvious. So what we got? We got the number of moles that is dissociating, and we got what is the number of moles which is left for HA. Our next mission is to see that what is the amount of product which is formed for H3O plus and A minus. How do we do it? So if we know that C alpha of mole is of HA is getting dissociated, then from the above balanced chemical equation we can easily say that the number of moles of H3O plus which is formed and the number of moles of A minus which is formed will be equals to C alpha. Why we are saying it? Because one equivalent of HA is getting dissociated to form one equivalent of H3O plus and one equivalent of A minus. So therefore, C alpha amount of HA will be dissociated to form C alpha moles of H3O plus and C alpha moles of A minus. So this should be clear to you. Now we can write the same thing in a tabular form. See, we have this initial concentration C. After some time, C alpha is getting dissociated to form C alpha of H3O plus and C alpha of A minus. Now we will continue with this table to get the value of K in terms of alpha. So this was the tabular form that we got. Now if you write K using this table, then we can write this thing as H3O plus concentration multiplied by A minus concentration divided by HA concentration. On substituting the values, we will get it as C alpha multiplied by C alpha divided by C into 1 minus alpha. Then you can take this C common, and finally the C will get cancelled out in the numerator and denominator to give you C alpha square by 1 minus alpha. You can further, what you can do, you can just approximate this K thing. How we can do it? So it's very simple. So there is a small approximation to this formula of K C alpha square by 1 minus alpha, in which we say that, okay, since your acid is getting dissociated to a very small extent, therefore this alpha will have a very small value, because alpha is nothing but the fractions of molecule getting dissociated. Now if this is true, then 1 minus alpha can be approximately written as 1. Further, we can write K as C alpha square only, or alpha is equals to root under K by C. So this is a very important formula, and this shows you the relation of alpha and K. In some cases, you will see that we take this equation also only, but in most of the cases, we take alpha is equals to root under K by C. So we have defined K and alpha relation in an approximate way. Further, we will calculate the H3O plus concentration. So this is important to calculate the pH. We are calculating pH, right? So we need H plus concentration for sure. Or you can say we need hydronium ion concentration. For that, we are doing a small assumption, which is this whole acidic solution is now kept to 1 liter. If this is so, then the number of moles will be simply equals to the concentration, because in the denominator of the molarity we have the volume, and now volume is kept to 1 liter, therefore number of moles will be equals to the concentration. So from the above table we can write that H3O plus will have a concentration of C alpha, but we know that alpha is equals to root under K by C. So we can write H3O plus concentration is equals to C into root under K by C, or K into C and root under K into C. Is it clear? So this is very, very important relation for you in the upcoming lectures as well. Now moving on further, if you want to calculate pH, then we know from the definition that pH is equals to minus log H3O plus. If we substitute H3O plus as root under K by C, that we can write pH is equals to minus log root under K into C. So this is your final relation. Next, we can similarly define the base ionization formulas for Ka and pH. So if we consider the table for the dissociation of base, then it will be simply C is the initial one, then C minus C alpha is at equilibrium, then C alpha is for the M plus concentration, and C alpha is for similarly for the OH minus concentration. Now, if I write the base dissociation constant similar to the acid dissociation constant, we can write it as Kb is equals to C alpha square by 1 minus alpha. And your pOH can be written as how much? Minus log OH minus, we know this thing, or we can write it as minus log root under Kb into C. What is Kb here? So Kb is your base dissociation constant. Similar to the K, higher the value of K, we have the stronger acid. So higher the value of Kb, we have a stronger base, or lower the value of Kb, we have a stronger base. So these two things are again true for the bases as well. Moving on to the next part, which is K and Kb. So I would say that this part is somewhat hidden part and a most important one also. So we will derive a relationship between K, Kb and Kw. Okay. And that relationship will be only true for your conjugate acid-base pair. How? Suppose we have a acid-base pair NH3 and NH4 plus, right? Now, if you consider first of all NH4 plus as an acid, then what will happen? This NH4 plus will donate a proton and will be converting into NH3. For this case, if I write K, then it will be hydrogen ion concentration multiplied by NH3 divided by NH4 plus concentration. Similarly, if we take NH3 as base, then in that case what will happen? We will have a Kb, not a K but a Kb, which will be NH4 plus concentration OH minus concentration divided by the NH3. Further, if we are taking these two equations for the dissociation constant of acids and bases, which is NH4 plus and NH3 specifically, then we got these two equations. Next, what we do, if you want a relation, you have to multiply K and Kb. So K multiplied by Kb will be giving you Kw. Very simple. This NH3 and NH3 will get cancelled out, and NH4 plus and NH4 plus will get cancelled out. So you will be only left with H3O plus multiplied by OH minus, but which is nothing but your Kw. Got it? Further, we can take a log base 10 with a negative sign, which will give you this same relation in terms of pKa, pKb and pKw. So this is your final relation for the pKa, pKb and pKw. Now let us summarize what we have studied so far. So ionization is basically molecules breaking into ions in a solution. And for a strong acid and base, it should dissociate completely. And for a weak acid and base, the dissociation is partial. Then we moved on to water, which is having a ionization constant as Kw. How do we define it? So we define it on the basis of equation in which your water is itself ionizing into H plus and OH minus, which is further reacting with another molecule of water. So if you want to define Kw, then it is simply the multiplication of H plus and OH minus concentration, and at 298 Kelvin this is equals to 10 to the power minus 40. Further, we defined for weak acids the value of Kb. So if you have a weak acid, then it will partially ionize to form its conjugate base, and K is the measure of that ionization. Higher the value of K, greater is the ionization, and lower the value of pK, higher is the ionization or greater is the strength of your acid. Further, we have a weak base. So weak base also ionizes partially, and Kb is the way to represent the strength of this ionization or the strength of the base. After that, we discussed about pH scale, which is a way to define the H plus concentration of a given solution in a much more convenient way, and it can be defined as a negative logarithm of the H plus. Further, If your solution is having a pH less than 7, then it is acidic. If it is equals to 7, it is neutral, and if it is more than 7, it is basic. So this is true at 298 Kelvin. Last, we derived a relation for Kw, Ka and Kb, which is only for conjugate acid-base pair. So it can be written as K into Kb is equals to Kw. So this was all for today's lecture. I hope you enjoyed the session. Thank you for joining it.